We start with some examples for comparison tests, direct comparison test and limit comparison test. So essentially we need to figure out which one of the tests is more appropriate or easier to apply. So in this situation here, we see that the general term of the series is this. So now we have n squared plus n cubed in the denominator. So essentially what we know is that the denominator is bigger here than here. So essentially we know that n squared plus n cubed is bigger than n squared. So we flip it, 1 over n squared is bigger than this one here. That's what we have. So this is our comparison series. Now here it's easy to see. We recognize that the series with B, so this is smaller than this series here. So now this series is a convergent P series. And P here is equal to 2, it's bigger than 1. So whenever we have a P series with the power P bigger than 1, then we know that series is convergent. So the bigger series is convergent, therefore the smaller series is convergent also. Obviously these terms are both bigger than 0, that's obvious. So the bigger series is convergent, therefore by direct comparison the smaller series is convergent. So by direct comparison test, our original series is also convergent. So that's straightforward. Now one note, here we had these two pieces downstairs, so we said that this is smaller than 1 over n squared, but it is also true that this is the case. So again, we would have a P series with P equal 3, it would be convergent still. So in this case, we have a choice between picking one or the other of these two expressions in the denominator to create our comparison series. In both cases, we would get convergent, so it doesn't matter really which one we pick in this particular case. However, let's say that I have a slightly different case. So I have these same things, except here, let's say I have n plus n cubed. So an is obviously bigger than 0, is n plus n cubed. The wise thing would be to say that this is smaller than 1 over n cubed. So this way we will compare this series to P series with P equal 3. It will be convergent, so that would be easy. So the series is convergent. P series with P equal 3, and 3 is bigger than 1, so it's convergent. Then the original series is also convergent, so there is no mystery there. And the tool we used is by direct comparison test. So that's straightforward, it's clear. Now, what happens if someone, by mistake, says that he would like to use 1 over n instead of 1 over n cubed? So that would be an interesting situation. We know that here, obviously, if an is n plus n cubed, is also smaller than, so I would call it Cn, is also smaller than 1 over n. That's clear. It's not a problem. However, the series that I have here, 1 over n, is harmonic series and it is divergent. So this is divergent harmonic series. So here is P is equal to 1 and is divergent. So we remember this P series, when P is strictly bigger than 1, it's convergent. But if P is 1 or smaller than 1, then the series is divergent. So now what we have is the bigger series is divergent. We cannot say anything about the smaller series, right? So that's a problem. So this is totally useless because all we have is smaller series here. This is smaller than something divergent. So this is not helpful. So this is divergent, not useful. We cannot conclude anything about this series. So no conclusion here. So that's why the choice that we make is important. If we make a bad choice, we will maybe get a divergent series, so bigger series is divergent. We cannot conclude anything about the smaller series. So we need to be strategic a little bit, try to recognize things in the expression. So we cannot just blindly write things because it's not really helping. Let's say we have another situation, slightly different. So let's say we have a series with the general term, so again it's positive obviously, 1 over ln n. Here we start at 2 because ln 1 is 0, so we don't want to divide by 0. So we start at 2. So some series will start with 1, some with 2, some with 3, doesn't matter. So this is our general term. So we would like to see what to do here. Can we compare it to something? Now we remember that log n is smaller than n. It's actually smaller than any power of n. Okay, so now what do we have here? Well, it's 1 over ln, so I flip them. Okay, so since ln is smaller than n, 1 over n is bigger, right? 1 over n is smaller than 1 over ln. Ooh, this is very good, because I know that this baby is a divergent harmonic series, and I will have here a bigger series. Yay! So Pn is equal to 1 over n. So what I have here is Bn, 1 over n, is smaller than An 1 over ln n. That's good news. So the smaller series, and again we start from 2. Let me do this for a moment. So the smaller series now is divergent, so this helps me conclude, right? Since this is here a harmonic series, so a divergent harmonic series, then by direct comparison test. The bigger series is divergent also. So here it was very important to observe that ln is smaller than n, and then 1 over n is smaller than 1 over ln. So this helped us. So the smaller series being divergent, the bigger series must be divergent also by direct comparison test. So that's just a useful observation. So now let's say I have a variant of this for fun. And in this variant, I will have a series, again starting from 2. I have ln over, let's say, n squared. What happens then? So again, if we say ln is smaller than n, then we say ln squared. ln divided by n squared is smaller than this, but this is 1 over n. We know that the series here is smaller than this series here, and then we will just realize how useless that is. So this is smaller than 1 over n. The fact that it starts from 2, it doesn't matter for the convergence. So this is divergent, right? Harmonic. Oops, the bigger one is divergent, so we cannot conclude anything about the smaller one. So this is not useful, because we cannot conclude anything about the smaller series. So now what do? We realize that this comparison, which worked here just fine, well, now here doesn't work really well, because if we use it, we get this comparison, and then the bigger series is divergent. It's no good. So what do? Well, we know that ln is smaller than any power of n. So let's say it's smaller than square root of n. Now it's more interesting. Square root of n. So what do I have here? N to power 1 over 2, and here is n to power 2. So I have 1 over 2 minus 1, so it's minus 2, sorry. Minus 2. So this is minus 3 over 2. So I have here n to power 3 over 2. Now it's nicer. Now I have something. Because here I'll have a p series with p 3 over 2, which is bigger than 1. So this is convergent p series. Is a convergent p series with, so here p is 3 over 2, which is bigger than 1. Since that's the case, that means that the smaller series is also convergent. Then, by DCT, direct comparison test, the series ln over n over n squared is also convergent. Okay, so here the key was to realize that ln is smaller than any root of n also. So these are some details that are important to observe. Let's consider an easy case here. So we observe obviously that the general term is positive. Now we know that 4 to the power n plus 2 is bigger than 4 to the power n, which means if we flip them, 1 over 4 to the power n this is bigger than, right? Is this true or not? So I have bigger thing. If I divide by bigger, I get something smaller, right? Bigger guy, 1 over bigger guy is smaller number than 1 over smaller guy, which means that this is smaller than here. So I can have my Bn actually as 4 to the power n, which is my Bn. So that's cute, that's easy. So now what happens here? What do we know? What about this series here? 1 over n to the power 4. 1 over 4 to the power n. What type of series is this? We rewrite just a little bit maybe to see better. 1 over 4 to the power n. So this is a geometric series. So we have 1 over 4 plus 1 over 4 times 1 over 4. So the first term will be 1 over 4a, and the second term is 1 over 4 times 1 over 4. So r is also 1 over 4. So here we have a geometric series. Is a geometric series with the ratio 1 over 4, and that's smaller than 1. So what do we know about the geometric series with the ratio in absolute value smaller than 1? Well, they are convergent. Oh, hence this series here, the geometric series, is convergent. Okay, so what does that mean? The bigger series is convergent, so the smaller series by direct comparison must be convergent also. So by direct comparison test, the smaller series is convergent, right? So our series here is convergent by direct comparison test. So that was straightforward, nothing special there. Now, just to see what happens, here I have plus 2, and here I have minus 2. 4 to the power n minus 2. So now, just to observe, 4 to the power n minus 2 is smaller than 4 to the power n. So I have something like this now, minus 2. So my b is this, but we just saw that this would bring us to the conclusion that this geometric series is convergent. So I have the smaller series is convergent, but I cannot say anything about the bigger series. So this is useless. Why? Because the smaller series is convergent. So what do we do in this case? We cannot use DCT is useless. So direct comparison test is a useless tool here. Okay, so we need another tool. That's what it means. So try limit comparison test. So we have our A still 1 over 4 to the power n minus 2. And then we go, okay, let me see dominant terms. So if I check the dominant terms, what do I get? Upstairs is 1, and downstairs I have 4 to power n. So those are two terms, so upstairs is 1 and downstairs is this. Okay, cool. We already know that this will give rise to a convergent geometric series. That's all beautiful. But in order to apply the LCT, so obviously these are positive numbers, both of them, nothing special there. So in order to apply LCT, we need to verify the condition. So must verify that the limit of the ratio of these two general terms is a positive real number. Okay, how do we do that? Well, it's not an issue. We just compute. So limit an over bn is equal to limit. So an is 1 over 4 to the power n minus 2, and bn is 1 over 4 to the power n. So this is equal to, here. So I have double fraction. So 4 to the power n minus 2 here, and then 4 to the power n upstairs. What do we do now? We will factor 4 to the power n here, downstairs, so that will be useful to simplify. So 4 to the power n factor of, so here is 1 minus 2 over 4 to the power n. So now it's cute. So let me here. So in this situation, the direct comparison test was not useful, and then we tried to have the limit comparison test. So this guy here will lead to this expression 4 to the power n, 4 to the power n is simplified. So upstairs I have 1, downstairs I have 1 minus 2 over 4 to the power n. Now, this term here will go to 0, so I essentially have 1 over 1 minus 0, 1 over 1. So this is bigger than 0, and it's a finite number. So now we see that we satisfy the condition of the limit comparison test. So now we can use the conclusion of this theorem. What does it say? Well, it says that both series either converge or both series diverge. So what do we know? That this series is convergent, therefore our series will be convergent also. Then I'll just write that either. So I'll write an and bn. Both converge or both diverge. By LCT, right? That's what it means. Well, we know that the series with B is convergent, therefore the series with A must be convergent also. That's the logic part. Since the series with B, let me just write the series with this 1 over 4 to the power n is a convergent geometric series original series must be convergent also. Is also convergent. So it was important to realize that here direct comparison test was not useful. So then we try another tool, which is limit comparison test, but that one has a special condition. We need to check the limit of the ratio of two general terms of our original series and the comparison series, and we figured out that that limit is a fixed number, here 1, which is bigger than 0. That was the condition. Since the condition is satisfied, we know by the result of limit comparison test that in that case both series are either convergent or both series are divergent. Here we recognized our comparison series was a geometric series with r equal 1/4, so 0.25, which is smaller than 1. That means that our comparison series, the geometric series, is convergent. Then by LCT, the other series must also be convergent, because both of them are convergent at the same time, or both of them are divergent. Now we know that our comparison series, we have an information about it, so that means that the same conclusion goes for the original series. So this is an important step-by-step process to realize that sometimes we cannot use direct comparison, we must use limit comparison. Here is another example. We have a series, here it starts from 2, the counting. So this series is given, the general term is again positive, and it's given by a ratio of two polynomials. Now for now we have two tools, direct comparison test and limit comparison test. So let's see what we can do here. If we go and try direct comparison test just to see what happens. So this thing is bigger than if I only have n squared upstairs. I keep the same denominator to simplify things slowly. So I have something positive plus something else positive. So that's bigger than just one of the guys. Okay, cool. So now I have the denominator. So I have n cubed minus 2. So this is smaller than n cubed. So the ratio is bigger than the ratio if I only had n cubed. So this is 1/n, right? So this is my comparison series. Now is this going to be useful? So I have the general term of my series, which is bigger than something which is bigger than 1/n. Wow, 1/n, that series is harmonic divergent, and my series is bigger than that, so my series must be divergent. So this is useful, great. So that's how I know I did a good job. So since this series here is harmonic series, divergent, right? It is a P series with P equal 1, so it must be divergent. Then by direct comparison test, since this baby is bigger, so AN is bigger than BN, right? Then by direct comparison test, the series, the original series, so n squared plus 2n over n cubed minus 2 is also divergent. So this one was useful and we are able to conclude. Now what would happen if someone would say, well, here you picked n squared, true, but you could have picked 2n also, true. As a general rule, we take the highest power the dominant term. But what would happen if we didn't? Then I would have my an, so n squared plus 2n, n cubed minus 2. So this would be bigger than 2n over n cubed minus 2. That's true. Now, by the same rule, this is smaller than n cubed, so the ratio is bigger than n cubed, which is 2 over n squared. So what would happen in this case, so let's call this Cn. In this situation, what do I realize? I have the general term of my series, which is bigger than general term of the series with 2 over n to power 2. So that would be here a p series with p equal 2. So that series would be convergent. My series is bigger than that. Oops, that's not helping me conclude anything about my series. The smaller series is convergent, but I don't know what's happening with the bigger series. So that's why this would not help us at all. So in general, you try to take the dominant term upstairs when possible, when you can have this type of comparison. Now, just to see how quickly things change just by changing one sign. So here I have n squared minus 2n. So it's not plus, it's minus. So the denominator stays the same. So now I cannot do this. Cannot do this. Because it's not true. If I leave this alone, if I drop it, actually, I don't have the sign on the other side. So it doesn't work. So I could say that this is smaller than n squared n cubed minus 2. That's true. Is that useful? Well, now if I want to get rid of this guy, the inequality would go the other side, and then it doesn't work. So you see the direct comparison is not going to be helpful here. Okay, so I realize direct comparison doesn't work. Fine. So I will not use it. What might work? Well, I will see the dominant terms. So this behaves as the dominant term upstairs is n squared, dominant term downstairs is n cubed. So this is 1 over n, so this is my Bn. And I will try to use LCT. Try limit comparison test. Obviously both of these are positive, an and bn. So what do I need to do? I need to first compute limit when n goes to infinity of an over bn. If this limit is equal to a number bigger than 0, then I satisfy the condition for limit comparison test. Obviously, the series with this general term is harmonic divergent. That would mean if I'm able to find the limit is something bigger than 0, a number, then I could use the LCT to conclude. Let's see what happens. an, so I'll have here double fraction over 1 over n. Okay? So this is equal to, if I bring it to a single fraction, n cubed minus 2. So this guy goes up. So I have n times n squared 2n. Distribute the n. N cubed minus 2 downstairs. So upstairs is n cubed minus 2 n2. The next step, divide upstairs and downstairs by the highest power of the denominator. So this means I would do the following. So limit as n goes to infinity, 1 over n cubed over. So I do step by step just to illustrate the situation. Fine. So now here, what would happen? I have 1 minus 2 over n cubed, and upstairs I have 1 minus 2 over n. Now the limit of this, limit of upstairs is 1, limit of downstairs is 1, so 1 over 1 is 1. So this is a fixed number, positive, greater than 0, cool. I satisfy the condition for LCT. Since the condition for LCT is satisfied, this is mandatory. We cannot use the LCT without checking this. I know it's annoying, but we must do it. So since this condition is satisfied, then both our original series and our comparison series are either convergent or divergent. So both of them, right, are both. Okay, so what can we conclude here? While we have this series here, which is a harmonic series, and we know it's divergent, therefore, so since the series Bn is actually 1 over n, which is a harmonic series, is a divergent harmonic series, then by a limit comparison test, our original series is also divergent. So I'll just copy it. So we see here the situation is a little bit different from the previous examples. Just by changing one sign, we need to change the two. Okay? But what matters is to check the condition for LCT. It's mandatory. We cannot avoid that. Another cute example. This time we have sine squared in the expression or general term of the series. So we know that sine squared is positive between 0 and 1, so that's good news. So our general term is given here. So we know that sine squared is at best 1 and at worst is 0. So the upstairs is smaller than n. We can put equal also if we want, doesn't matter. And downstairs remains the same. Now here we analyze the situation and we see that n cubed plus 1 is bigger than n cubed. So when we divide up by a bigger number, we get a smaller result than if we divide just by n cubed. So here it simplifies and we get 1 over n squared as our comparing series. Now that's good news because 1 over n squared is a convergent P series with P equal 2, so that's good news. Then by direct comparison test, since the bigger series is convergent, then the smaller series must be convergent. So that's helping us to conclude that our original series is convergent as well. Now, just one small change. Instead of n cubed plus 1, we have here minus 1. So that would prevent us from doing this. Here. It will prevent us from making this constatation. The inequality would be in the other side, so that's not useful. So DCT would not apply here because of the minus. So okay, let's try limit comparison test. So we have our comparing series Bn, and we know that this series will end up being convergent, but we need to first check the condition for LCT. So limit of the ratio of the coefficients. So we have this big double fraction. So this with this, and then this guy with the upstairs. So we have n cubed. Now again we factor n cubed. So we get this expression. Now we can simplify them. So we end up with this expression here with sine squared upstairs and the denominator 1 minus 1 over n cubed. So when n is big, this goes to 0, so the downstairs goes to 1. No issue at all. But what happens with the sine squared? So we put here numbers 1, 2, 3, 4, 5, 6, and we keep going. We will realize that sine squared is actually oscillating, so it doesn't converge to any specific real value. Oops! That means that this limit here does not exist. Oh my god. The condition for LCT was that the limit here exists, it is a number, and that number is positive. Well, this expression is positive, but the problem is it keeps oscillating, it doesn't converge. Sine squared and does not converge to a fixed number. So the limit does not exist. Uh-oh, what do we do? Well, that only means that the condition for limit comparison test is not satisfied. What does it mean? Well, we cannot use the limit comparison test. Oops. So our second tool doesn't work. You see, I just changed one sign from plus to minus, and suddenly our two miraculous tools, direct comparison test and limit comparison test, well, in this situation, none of them works. Ta-da! So it's important to realize that sometimes our tools just don't work. That's why we will discover more tools in future. Here another example. We have a series with a complicated general term. Is a third root of a polynomial. So what we realize is, what we realize is that because of the plus here, we can actually say that the downstairs is bigger than without the 3, so the ratio here is smaller than this part here because plus 3 is missing. We could take 4 separately, so third root of 4, and then n to power 4 over 3. This is just to see a little bit better what type of series we are going to have. So here, this is a direct comparison. So since this series here, so this is a number, right? The constant, we can take it outside. This series here is a p series, and p is 4 over 3. 4 over 3 is bigger than 1. So by direct comparison test, this series is convergent because our p series is convergent. So that was easy because of the plus here. So I removed the plus, I put minus just to see what happens. So now because of the minus, I cannot say this anymore. So we cannot use the comparison test in the case here with the minus. So what do? Well, we try limit comparison test. We try to find the dominant terms. So upstairs is 1, and downstairs the dominant term is 4n cubed third root. Okay, third root of 4n to power 4. Okay, so I just split it a little bit. We don't need to in this case, but just to see a little bit what's going to happen is the same situation as previously. Now we need to check the condition for limit comparison test. So limit of ratio of the general terms when n goes to infinity. So we have double fraction as usual. We bring it to a simple fraction. So we have here. Now, usually what we do, we want to simplify things. So we will try to factor 4n to power 4 here in this root. It's not a problem, we can always do that. So the first term becomes 1, and the second term becomes minus 3 over 4n to power 4. Okay, so now what happens, we have a times b, right? So we can separate them. Why? Well, because this is the same expression, so we can simplify. So 4 third root n to power 4 third root. So they simplify these two, and we end up with 1 divided by here, still 4 missing. So at the end, this is the expression. We compute the limit. Well, the limit of this term is 0, so 1 over 1 is 1, and it's strictly bigger than 0, so we have the condition satisfied for limit comparison test. That's cool. That means that the series with this general term and the series with just general term, they both converge or they both diverge. So since our comparison series is something that we know, it is a P series with P 4/3, which is bigger than 1. That means that our P series is here convergent. Therefore, our original series is also convergent by limit comparison test. So the steps need to be produced, and we need to compute the limit properly. Other interesting examples. Here we have a series with a very complicated general term. Now, as we are used to seeing when we have plus, 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 these positive terms downstairs, that would mean that this expression downstairs is bigger than if we keep only one piece. As usual, we keep the dominant expression. So here we will keep n cubed. Okay, because of the pluses, we can write this inequality. Because with plus positive, the denominator is bigger than just with one of them. Which means that this ratio here is smaller than this ratio here. Because here the denominator is smaller, so the ratio is bigger. Now here we have n to power 1/3, so third root. And here is n cubed divided by 2, second root. Now we need to combine them together. So the powers, we have n to power 1/3 minus 3/2. So 1/3 minus 3/2. So common denominator is 6. So we have here 2 minus 9. So that's minus 7/6. So we have n to power minus 7/6. So 1/n to power 7/6. So the negative would bring n down. So this is our comparing series here, Pn. Now we have our general term, positive obviously, be smaller than a term of a comparing series. Now we are lucky here 7/6 is bigger than 1. So this is a P series with P 7/6 bigger than 1. That means that our P series is convergent. So we have our series will be smaller than a convergent series. So then by direct comparison test, our series must be convergent as well, because it's smaller than convergent P series. So that's straightforward. Obviously, if we had minus here, we couldn't do this, so we would need to go to limit comparison test. As soon as one of these two is minus, we must go to limit comparison test. Now, another interesting example here, obviously it is a little bit built in a special way. We are used to going with our comparisons in one direction. It's always smaller or equal. So let's see here a little bit what's happening. So we have this expression. Now the new thing is, by increasing the denominator, the value of the ratio will decrease. So instead of 1 here, I put n. n is bigger than 1, obviously. So my denominator here is bigger than denominator here. So the ratio, if I divide something by a bigger number, is going to be smaller. That means that my an is bigger than this expression here. Now the good news is we can factor n. So 1 plus en, 1 plus en, they simplify. So I have 1/n. It's very fortunate. So I have my expression for the general term from the original series is bigger than the term of the comparing series. Now we are lucky that our comparing series is divergent harmonic series with power 1 here, right? Therefore, we have a divergent harmonic series, and our series is bigger than that. So by direct comparison, our series must be divergent as well. So here what was interesting is that we increased the denominator by replacing 1 by n conveniently, and then it factored out, and then simplification happened. And then we were lucky that actually we had 1/n, so the series that we get is harmonic series, which is divergent. It helps conclude. So this is very special case, but just to see that actually we can sometimes increase the denominator, because in general what we are doing here, we are diminishing the denominator to get something bigger. Here what we did is increase the denominator to get something smaller. Okay? So that was an interesting example to open our eyes a little bit. Another interesting example, series with the general term 1 over n to power n. Ooh. Now we just need to observe then that 1 over n to power n is more than 1 over 2 to power n, because obviously n to power n is bigger than 2 to power n. It's also bigger than 3 to power n, so I just choose one of them that does the work. So the downstairs here, the denominator is bigger than the denominator here, that's why the ratio here is smaller. Okay? N to power n is ginormous, is bigger than 2 to power n, obviously, so 1 over, we have this. So now we have our general term and the general term of a comparing series. We realize that this will be a geometric series with common ratio 1 over 2, which in absolute value is smaller than 1. That means that this geometric series is convergent. We already know that. So our series will be smaller than a convergent geometric series. So then by direct comparison test, our series is also convergent. Ta-da! Now an interesting case, here we have 1 plus cosine n divided by exponential n. Observation, cosine n, obviously it's between -1 and 1, but it's not -1 or equal to 1. Why? Because the coefficients here, the arguments are 1, 2, 3, 4, 5, right? So the only way for cos to be equal to 1 is cos 0, cos pi. Well, we don't have n equals 0. Pi is irrational number, so there's not much we can do about it. So essentially 1, 2, 3, 4, 5 will never produce cosine equal to 1 or -1. So that's why I keep the strictly smaller signs. Now our expression upstairs is 1 plus cosine, so I use this inequality and I add 1 on each piece. So plus 1 here, plus 1 here, plus 1 here. So we have 0, 1 plus, and here 2. Now the final expression is divided by exponential n. So again 0, this is our expression, and it's more than 2 to power en. Now 2 is a constant, can go outside of the series. We recognize that this will be a geometric series with a ratio 1 over e. So 1 over e is 2.7, so 1 over e is smaller than 1. So this will be a convergent geometric series. So what we have now is the general term of our expression smaller than a term of a geometric series, a convergent one. So this series is bigger than this series here. Therefore, by direct comparison test, since the bigger series is convergent, our series is also convergent. So straightforward computation and logic. An important observation. So let's say that for some reason we have a series with the general term cosine n. So cosine n obviously is 1, 2, 3, 4, 5. So if we compute a little bit, and it's in radians, right? The argument of cosine is and sine is in radians. So if we compute a little bit, we will see that systematically we can have positive and negative numbers depending on the value of n. So cosine of n, as we change n, sometimes it's going to be positive, sometimes it's going to be negative, then positive again, then negative again, then positive again. So we keep generating positive and negative numbers. Well, that means that we cannot use the direct comparison test or limit comparison test on this series. Why? Because both of them require that the general term is positive, at least from certain point on. So maybe your first 2, 3 terms are changing sign, and then after that everything is positive. That would be okay. But in this situation here, we generate systematically along the way positive and negative numbers. So there are infinitely many of these negative numbers here. So the general term of this series here would be sometimes positive, sometimes negative, and systematically like that. Therefore, it's not positive, so we cannot apply the direct comparison test, and we cannot apply limit comparison test. It's important. Another variant is cosine n or sine n divided by e to power n, for instance, or 2 to power n regardless. Again, the e is positive, exponential of n is positive, but cosine again generates some positive, some negative numbers. So our general term will be sometimes positive, sometimes negative, and these positive and negative numbers are generated systematically. Therefore, the general term is not positive, therefore we cannot use direct comparison test, and we cannot use limit comparison test. So you see, if I put a square here, things change and simplify. But cosine as is, it's a problem. If I put power 3, well, still I will have these generation of these negative numbers, so it will not be okay. So you see, we change a little bit the expression, and suddenly our tools don't work anymore. So we need different tools eventually. Another funny example. Here we have a very special series with a very complicated expression for the general term. So just before we start, just to see why the direct comparison test doesn't work here, if I try to apply it, I can always say that the upstairs here is bigger than the upstairs here. So we have something in this direction, which is fine. But now the problem is that 2 plus n is bigger than n. So this ratio here is smaller than this ratio. So now I have a problem because I have conflicting directions. I cannot say that this is bigger than this, obviously. So this is completely useless. If I try to do it by direct comparison test, I have a serious issue and I cannot do anything. Because this expression is smaller than this, but this expression is bigger than this. So I don't know who is where exactly here. So this type of comparison doesn't work. So direct comparison test, we drop it, nothing to do here. It's totally useless. So we need to be very aware of the situation when we have conflicting directions of the inequality. That means things don't work in that direction. So because of that, I need to use my limit comparison test. And how does it work? Well, we take the dominant expression from the dominant term from the upstairs, which is radical n. Obviously 1 is not the factor here. And then the dominant term from the downstairs is n. So I have radical n over n, which is 1 over radical n. And I rewrite it this way, it will be useful later on. So I have my general term from my original series, and then I have a general term for the comparison series here. So since I'm trying to do the limit comparison test, I need to verify the condition. So now ratio of general terms, so we have again double fraction, so we rewrite it. So this guy goes up, this stays down. So I have radical n times radical 1 plus n. So I can regroup it together, so I have n times 1 plus n in the radical, so n plus n squared. Now I will factor n squared in this expression. So the first term will be from n, it becomes 1 over n. So why do I do that? Because I need to simplify things. I need to compute this limit. So n squared radical, n is positive, so n is here, fine. Now, in the denominator I'll factor n also, because then I will be able to simplify. So if I factor n, I'll have n factor of 2 over n plus 1. So now n and n can go, and I have this expression. So now it's easy to compute the limit. Limit of upstairs is 1, limit of downstairs is 1. So the limit of the ratio is 1, which is bigger than 0, it's a fixed number, that's beautiful. The condition for my limit comparison test is satisfied, so now I can use the result. What does the result say? Well, it says for limit comparison test that my original series and the comparison series are both either convergent or divergent. Now, good news is my comparison series is a P series with P equal 1 over 2. 1 over 2 is smaller than 1, and we know that that P series must be divergent. So by comparison test, the other original series must be also divergent. So that's what we do, we apply. And again, it's important to realize that your signs don't go always in the same direction. In that case, you need to drop it. You cannot use the direct comparison. Another interesting example, a series with a general term n plus 3 to power n divided by n plus 2 to power n. Here again, we cannot use the direct comparison test. We try with the limit comparison test. So the procedure as usual is to find the dominant term in the numerator and the dominant term in the denominator. So upstairs the dominant term is 3 to power n, obviously. Exponential is bigger than polynomial degree 1. So 3 to power n, and downstairs the dominant term is 2 to power n. So just to write it together, 3 over 2 to power n. This will be useful later on. So I have my original general term and then general term for comparing series. Now we try to apply the limit comparison test, which means we need to check the condition first. So the limit of the ratio of these two general terms. So we have, as usual, double fraction. We rewrite it as a single fraction. Now here we will factor the dominant term as usual from the bracket. So I have my 3n outside, so n divided by 3 to power n plus 1. And downstairs I factor the dominant term, which is 2 to power n also. So this way I see that I have 2 to power n, 2 to power n, 3 to power n, 3 to power n, so they will simplify, and I end up with this expression here. We know that the limit here will be 0, we need to compute it, but okay. So limit upstairs is 1, limit downstairs is 1. So the limit of the ratio is 1, which is bigger than 0, so the condition for limit comparison test is satisfied. So now we can apply the result. The result says that both series are either convergent or divergent together. So now comparing series, we realize that we have a geometric series with ratio 3 over 2. 3 over 2 is 1.5, which is bigger than 1. And we know for geometric series, when the ratio is bigger than 1, these series are divergent. So this geometric series is divergent, therefore by limit comparison test, my original series must also be divergent. So that's the procedure. Now an intermediary step to compute the limit of this expression and this expression. So essentially what we do, we must convert this into a function of x. So we use the associated function, essentially we replace n by x. So x here is a real number. And then we will use eventually L'Hopital's rule. So to compute the limit of this expression, we will start computing the limit of x over 3 to power x. We see that we have indeterminate form infinity over infinity, so we can use L'Hopital's rule. So the derivative of upstairs is 1, the derivative of downstairs is 3 to power x times ln 3. So now when x goes to infinity, this guy here is exploding, so 1 over goes to 0, so limit is 0. Since limit of this piece is 0, limit of 1 plus the piece is 1 plus 0, so it's 1. Similarly, we do the same procedure for n over 2 to power n. We convert it into associated function of a real number, and then we proceed. Last couple of examples. We have a general term that is a little bit special. What we notice is exponential to power minus n, so that means we can rewrite it with exponential downstairs. So now we have a fraction. Again, we need to think a little bit and see what to do in this situation. It's not really useful to use the comparison. We could, but it's more fun maybe to do the limit comparison test. Just rewriting it, so the dominant term upstairs is obviously 1 over n goes to 0. Downstairs is exponential n. So I rewrite 1 over exponential n like this because it will be useful. So this is a general term of our comparing series. Now, if we try the limit comparison test, we compute the limit of the ratio. So A and B. So we have double fraction as usual. We will simplify these two. So now it's straightforward. The limit is 1. So the condition for limit comparison test is satisfied. Now we observe that the comparing series is actually a geometric series with R equal 1 over E. That's smaller than 1. So our geometric series is convergent. Yay! So limit comparison test tells us that both series are either convergent or divergent, and we know that our comparing series is geometric and convergent. Therefore, by limit comparison test, the original series is also convergent. This one is a little bit funny. It's too easy. So what we observe here, general term, is exponential 1 over n divided by n. Now here, just a little bit of reminder, exponential of 1 over x. So n goes from 1, right? So when we start at 1, this is exponential of 1, so it's e. And then after that, it goes down, down, down. As x increases, this goes, so the exponent goes to 0, so e to power 1 over x goes to 1. So we see that this expression is always bigger than 1, right? So we have this from 1 to 0. It's the other way around. Okay. And then we have this comparison. Now here, what happens is this guy here is divergent because it's harmonic series. We know that. So by direct comparison test, our series is bigger than the harmonic. So original series is bigger than harmonic series. So the harmonic is divergent. Therefore, by direct comparison test, our original series is divergent as well. So just simple observation, nothing special there. Here, a very curious general term, 1 over factorial n. So n factorial, so it's 1 times 2 times 3 times 4 times 6 up to n. We can observe that n factorial is bigger than 2 to power n minus 1 just by plugging numbers a little bit. We see that. I put equal, so we don't need to put any restrictions on n, so it's fine, doesn't create any issues. So now this is bigger than this, so if I flip them, 1 over is bigger than 1 over n factorial. So our general term is smaller than this piece here. So I rewrite this a little bit, because this is what it is, just to simplify my expression at the end. So I have my comparing series with a term here 2 over 2 to power n. I can take 2 outside, obviously. And now what I see here is our well-known geometric series with ratio 1 over 2. 1 over 2 is smaller than 1. So this geometric series is convergent. So we observe that the bigger series is convergent, therefore the smaller series by direct comparison test is also convergent. those are some of the examples that we have here, just to make sure that we observe things properly. Sometimes we use limit comparison test, sometimes direct comparison test. It depends on the situation. And we saw also some examples where none of those tests help us to conclude to the divergence or convergence of the series. That's why we need more of these tools, more tests that we will see later.